Okay. Today I'm going to go with my seventh video, Demystifying C. It is a separate playlist that has been created for relieving all the doubts regarding how to code a C program efficiently. Why do we declare a variable of a particular data type? Why do we call the parameters using a parameter, call a function using parameters and call a function using reference? How to decide whether data of given type is required for a particular program? All these things will be totally cleared through all these videos. So this video aims at providing deep-rooted analysis of existing C programs and enable the viewers to develop their own C programs. So with this basic introduction, let me start my presentation. So the name of the topic what I'm going to provide is Demystifying C. So the first topic which I'm going to deal is data types in C. Actually, this is a three-part video. In the first part, we will be dealing what is the basic definition of a data type, variable, constants, and how a given data, a given binary data will be stored in a memory location. And what are the different types of data that are supported by a microprocessor. So this will be the basic introductory video on demystifying C. So let us go into it. So data type, if you see, means it has totally five different definitions for it. First one, it is a value that is stored in a memory location. Next one, it can be, the value can be either a variable or it can be a constant. Or else, a data type is represented by the number of bytes it is going to occupy. So, a data type is the number of memory locations that are allotted to a user input data. Or else, it can be a value returned by a function on complete. That means, for example, there are two functions. One function will be have one program. Suppose there are two programs over here. One program is calling the function present in another program. So when the function in program number 2 is finishing the task that is posed by the function in program number 1, it will be returning back here integer value to the function in program 1 to indicate it has completed the defined task. There will be two programs over here. Suppose a function in program 1 wants to communicate with a function in program 2. It will be doing it by means of function call. Suppose the program function in program 2 wants to communicate to the program in the function in program 1, then it will be doing back by means of a return operation that indicates that it has completed the task defined by the function in program 1. Or it can be a value that is associated with a pointer. So pointer is basically a memory location which holds the address of another memory location. So pointer is also a variable. So variable is a name of a memory location. If one memory location holds the address of another memory location, means it is called as a pointer. So using a pointer to access a memory is only called as indirect addressing mode. This you might have studied in 8085 processor or 8051 microcontroller, or in case of electronics and communication people, computer science, they would have come across 8086 for them. they might have come across this word indirect addressing mode. That means if I want to change a value present in a memory location, and instead of directly accessing the variable, what I'm doing is I'm holding the location of another location in one particular memory location. That means one memory location will be holding the address of another memory location. Suppose there are two memory locations, one is called A, another one is called B. I want to make a change to the value that is stored in B. So if A is holding the memory location B, suppose if I want to make any changes to B, if I am making the changes to the pointer, automatically it will be reflected in the value present in B. A and B are two variables. B is one memory location. A is holding the B. B is one memory location. A is holding B. Suppose if I am making any changes to A over here, that corresponding changes will get reflected in the value present in B. So that is the meaning of a pointer. Another one, value associated with a constant. A constant indicates the value present in a memory location, or the group of values present in a memory location will never change throughout the program. Accordingly, a variable is called as a L value. A constant is called as a R value. Why it is called L value, R value means generally whenever we are declaring a variable and assigning it a value to it, a variable will be always on the left hand side of the assignment operator, so it is called L value. Whereas the constant which you are going to assign to the variable, that will be always present on the right hand side of the assignment operator. So because of this only we are calling the variable as L value, constant as R value. So variable indicates the value or a group of value present in a group of memory locations, or a value present in a memory location is capable of changing. Whereas if I am going to say a memory location is constant, it indicates the value in the memory location will never change till the end of the program. So next one, what are the different types of data that could be executed by a microprocessor circuit? So n-bit data that could be executed by a processor. That means executed means over which an operation can perform over which a processor can perform an operation is called as a word. So word is a generic term to indicate any n-bit data. Okay. So with this, we'll be seeing what are the 4 different types of words that are supported by a processor architecture. First one is byte. A byte represents group of 8 bits of data. A group of 8 bits of data. A bit refers to either logic 1 or logic 0. Alternately, a byte can be represented as a combination of 2 hexadecimal digits. One hexadecimal digit is equal to 4 bit. So 2 hexadecimal digits will be giving me the 8-bit data. So the processor which is going to execute which is going to perform operation on a 8-bit data is called as a 8-bit processor or a 1-byte processor. Example of 1-byte processor is 8085, 8051, PIC16C6X, PIC16C 7X. These are all consist of CPUs which operate on a 8-bit of data. Additional one information is the byte indicates the number of memory locations required for storing a particular data. For example, if I am saying a 1-byte processor means it will be acting only on one memory location or on a pair of one memory location. Whereas if I am going to say 2-byte data means it will be operating on a 16-bit quantity. So 2-byte means the data will be occupying 2 consecutive memory locations. So a 2-byte data can be viewed as a combination of 2 8-bit data, or it can be viewed as a combination of 4 hexadecimal digits, AA, BB. Here that A and B can be any combination of the hexadecimal digits varying from 0 and ending at F. In a 16-bit data, the leftmost 8-bit data is called as most significant byte. The rightmost 8-bit data is called least significant byte. So the processor which could perform operation on a 16-bit data is called as a 16-bit processor. Example is Intel 8086, Intel 8088. So these are the examples of 16-bit processor. Next one, we are coming to double word processor or double word, which is nothing but a 32-bit quantity. In terms of byte means it requires 4 bytes to represent a 32-bit value, or in terms of hexadecimal means it totally requires 8 hexadecimal digits to represent a 32-bit data. So as usual, in a 32-bit data, the leftmost 8 bits is called most significant byte. The rightmost 8 bits is called least significant byte. So for storing a 32-bit data, we require totally 4 consecutive memory locations. So any processor which is capable of handling 4 memory locations at a particular instant is called as a pair of 4 memory locations. Any processor which could handle a pair of 4 memory locations at an instant, it is called as your 32-bit processor. Because each memory location as far as present now can hold only one 8-bit of data at a particular location. So if I want to store a 16-bit data, I have to consider 2 consecutive memory locations for it. Similarly, if I want to store a 4-byte data means I have to consider 4 consecutive memory locations. Similarly, if I want to store a 8-byte data, I have to consider 8 consecutive memory locations. So these are the various considerations as far as you're storing your data in your microprocessor memory. So a quad word is nothing but a 64-bit quantity. In terms of byte means it totally consists of 8 bytes. Whereas in terms of your hexadecimal digit, to consider means it totally requires 16 number of hexadecimal digits to represent a 64-bit quantity. A 64-bit quantity totally requires 8 consecutive memory locations for its storage. So a microprocessor which is capable of handling a pair of 8 memory locations at a particular instant is called as your 64-bit processor. Example of your 32-bit processor will be Intel 80386, Intel 80486, Intel Pentium. Whereas if you come for 64-bit, you will be having AMD Ryzen, Intel i7 core, Intel i5 core, Intel i9 core. All these will be coming under 64-bit processors. So any processor which is capable of handling a pair of 1 locations, that is 8-bit data means it is called as a 8-bit processor. Any processor which is capable of handling a pair of 16-bit data means it is called as a 16-bit processor. Any processor which is capable of handling 2 32-bit datas at a particular instant means it is called as your 32-bit processor. Any processor which is capable of handling 2 64-bit data at a instant or a pair of 8 memory locations at a instant means it is called as your 64-bit processor. So here handling it refers to the arithmetic logic unit present in your processor because it is the unit which is going to accept the data, perform the operation defined by the instructions given to the processor, then provide the output. So a data handling capability circuit is called as your arithmetic logic unit. So based upon the data width of the arithmetic logic unit only, you will be naming a processor to be either a 8-bit processor or a 16-bit processor or a 32-bit processor or a 64-bit processor. If your microprocessor has a 8-bit ALU, it is a 8-bit microprocessor. If your microprocessor has a 16-bit ALU, it is called as a 16-bit microprocessor. If your microprocessor has a 32-bit ALU in it, it is called as a 32-bit microprocessor. Finally, If a microprocessor has a 64-bit ALU in it, it is called as a 64-bit microprocessor. So here also the leftmost in a 64-bit data, the leftmost 8 bits is called most significant byte. The rightmost 8 bits is called as your least significant byte. So these are the various examples to illustrate how does what is the least significant byte and most significant byte in different types of data. 65, it is a 1 byte data because it is a combination of 2 hexadecimal digits. Next one, we are going for 0x2654. Here 54 is the least significant byte, 26 is the most significant byte. So it is a 16-bit data. Combination of 4 hexadecimal digits will be giving me one 16-bit data. Next hexadecimal value is 45, 65, 23 AB. Here, this is a 4-byte data over here. A 4-byte data requires 4 bytes. That means 4 8-bit data or a combination of 8 hexadecimal digits. Here 45 is the most significant byte, AB is the least significant byte. Next one, if we come for the 8-bit data, the 8-byte data over here, 65 will be the most significant byte, 45 is the least significant byte. When we come to the 10-byte data over here, a 10-byte data requires totally 10 8-bit values. Okay, 10 byte means 80 bits. Here A7 is the most significant byte, 11 is the least significant byte. And at the last, a 16-byte data is given to you. 16-byte data means it is totally 128 bits in length. So here CF is the most significant byte, 1A is the least significant byte. So a 128-bit data will be totally containing 16 8-bit values. A 10-byte data will be containing totally 10 8-bit values. A 8-byte data will be containing totally 8 8-bit values. A 4-byte data will be containing 4 8-bit values. A 2-byte data will be containing 2 8-bit values. Finally, 1-byte data will be containing only 1 8-bit value. So, next one, what is the relation between the number of address lines emitted by a processor and the number of memory locations it can access? So, direct relation is the number of memory location is given by 2 to the power n, where n is the number of address lines. So, if the address line is 10, the number of memory locations will be 2 power 10. Which is nothing but equivalent to 1024. This 1024 in shorthand form is represented as 1K. Next one, if there are 11 address lines, then the number of memory locations the processor can access is 2 power 11. 2 power 11 is nothing but equivalent to 2048. 2048 in shorthand it can be represented as 2 into 1024. So 1024 has already been defined as 1K. So 2 into 1K will be giving me 2K. Similar is the case for the remaining address lines and their shorthand representations. Finally, in 65,536, there are totally 64 into 1K. 65,536 is the total number of memory locations. So 65,536 can be represented in short form as 64 into 1024. 1024 is nothing but equivalent to 1K. So 64 into 1K will be giving me 64K. So each location in a memory can hold only 8 bits of data. 2-byte data means 2 consecutive memory locations will be utilized. 4-byte data means 4 consecutive memory locations will be utilized. 16-bit data means 64-bit data means 8 consecutive memory locations will be stored over here. So as far as your C program is concerned, we will be mainly concerned with one is called static RAM, another one is called your dynamic RAM. So a variable or a constant will be mentioning, giving the, will be whenever you want to determine the address of a particular variable, what is the address of your memory location? That means a variable is the name. What is the address allotted to that particular variable means it will be automatically pointing to the address of the least significant byte. Suppose there is a n byte data, the leftmost 8 bytes is called as your most significant byte. The rightmost portion is called as your least significant byte. The address where the least significant byte is stored, that will be the address of the variable. That I will be showing. There are two ways by which a data can be stored in a memory location. One is called your little end, another one is called your big end. In little end, what we'll be doing means the least significant byte will be stored in the smallest address, that is at the little end. Most significant byte will be stored at the big end, which is nothing but your highest memory address. So to illustrate this, what we are doing, the least significant byte will be stored in the lowest memory address. The most significant byte will be stored in the highest memory address. Suppose I am having a data like this 0x78543268. This is totally a 32-bit data over here. 4 memory locations I am considering 0x54326543, 54326544, 54326545, 54326546. Here the memory location which is having 3 is the least smallest memory location. So over here we'll be storing the least significant byte of the data. So in this data 68 is the least significant byte, 78 is the most significant byte. The remaining intermediate values will be stored in the successive memory locations, that is in the growing order. For example, 43 will be holding, the location which is ending with 43 will be holding 68. The location which is ending with 44 will be holding the data 32. The location which is ending with 45 will be holding the data 54. And finally, the location which is ending with 46 will be holding the data 78. So 78 is the least significant, most significant byte. 68 is the least significant byte. So the values will be entered into a memory location in the ascending order. That means starting from the lowest memory address to the highest memory address. So this is the way how all the C programs will be, the variables or constants associated with the C program will get stored over here. So C programs, Java, Python, everyone will be following only little end. Little end means least significant byte in the least address, most significant byte in the highest address. Big endian is just the opposite of it. A least significant byte will be stored at the big end. Big end means highest address. The most significant byte will be stored in the lowest address. It is just the opposite of little endian. So the same data I am considering over here. What they have said, least significant byte at highest address. So 68 is the least significant byte that will be stored in the location 46. Then followed by it 32 that will be stored in the next lower memory location, that is 45. Then 54 will be stored in the memory location ending with 44. And finally 78 will be stored in the memory location represented by 43. So the values will be filled in the descending order, that is from the highest memory location to lowest memory location. So these are the two ways by which a data can be stored in a memory location. So with this I am concluding the basic contents about a data type. If you have any doubts, please kindly send me the comments. I will be replying to your doubts. So with this I am concluding my session over here, and thank you.